second one is
all right. So, question one. So I'm showing you what's called hot stage microscopy of a polymer melt. And so this is a hot stage that is clearly going to be able to melt polypropylene. So polypropylene melts at 160 C. So it's a pretty hot stage. And then they start cooling that off, that polypropylene film. And when it's amorphous, it looks like this pinkish color. It looks like nothing because there's nothing there to stop the light or diffract the light in any way. It's fully amorphous. We start cooling it off, and then at specific points in this film, this amorphous film, we see crystallization occurring, all right, recognizable as those nice round things that are doing interesting things to the light that passes through them. This is not plain polarized light, but you can still see some of that Maltese cross pattern we'll talk more about today. Okay, and so of those two regions, hopefully you guys are only seeing two regions in this image, which has the higher entropy?
darker red.
The what?
Darker red area.
Darker red area? Can you give me a more descriptive?
Not the crystallized area.
Not the crystallized area. Okay, that helps. All right, yeah. So that big blank space contains polymer chains that have not crystallized. All right, so that means that they have a much larger number of configurations because they're not forced into a crystal structure in which they have only one configuration. So it makes sense that this blank region has the higher entropy. Okay, and as you've learned before, and we'll go over it again today, crystal structures, yeah, they're crystalline, but they also have amorphous content. All right, but on average, there are definitely a much larger number of configurations in that blank space than there are on the crystalline region. Does that make sense? Again, focusing on the randomness issue. That's what we're talking about here. Any questions about that? Everybody got it right? Some, yes? All right. Okay. And then question two. Assume the CH3 side group that we know exists in polypropylene is replaced with something you've seen before, CnH2n plus 1, where n varies in this case between 1 and 3. So it's polypropylene sometimes, and then it's something other than polypropylene. This is different from LDPE, which n varies from, n and LDPE varies from what to what? 3 to 5. Okay, good. So this is not exactly that same formula. Under crystallization conditions identical to those shown above, what would happen to the percent crystallinity? Increase or decrease?
I would say increase, is that correct?
No, it's going to decrease. Why is that? Yes?
It's because since there's the variability, your puzzle pieces won't fit together as easily as before.
That's right. So every puzzle piece is no longer just CH3, which is what you get with polypropylene. It's now CH3 and C2H3. CH2, CH3, or CH2, CH2, CH3, because n varies from 1 to 3, right? And so it's one of those three configurations, but they're no longer all the same. All right, the puzzle pieces are going to vary a lot, so you'll probably get zero crystallinity when n is doing that. It will stay a blank space, no matter how quickly you cool it, or how slowly you cool it, or whatever, because of that variability. Okay? Hopefully that makes sense. All right, so this is how we control the behavior of polymers. If it's amorphous, it's more flexible than if it's crystalline. And so by changing this rule of what goes into the feed to make this polypropylene, we can make it completely amorphous and have different properties than if we let it crystallize. Okay, any questions about that? Hopefully it makes perfect sense. All right. Go ahead and make sure your names are on those and pass them forward. Well, passing out these notes. Thank you. Okay. Thank you. Thank you. Thank you. All right. So today we're going to start off talking about temperature and solubility, and this kind of picks up from where we left off last time in terms of this idea that temperature is important to us, and temperature in polymers is motion. So if we go back to where we were last time, first off, increased kinetic energy of the solvent can be important, and then more molecular interactions with a solute are part of this process. And so as you'll recall from last time, we have an interface. There they are. We have this interface, and let's just choose get yellow. So we have a polymer chain that is trying to dissolve out of the interface. And so there's a bunch of polymer coils inside this thing, and some of them are coming out. And you recall the convenient cheat I used last time where the solvent molecules happen to be these nice circular things in this system. All right. And as you also recall, if the polymer dissolves in the solvent can also dissolve in the polymer. And you saw data proving that. So we have some solvent going into the polymer, at least to a certain depth. And so this is the situation in which we find ourselves. And the effects of temperature are going to be important because this means increased motion of the polymer chains themselves. And we'll talk about that more today. But what we've got going on at this interface, let me pull this back over so you guys can see it still. What you've got going on at this interface is this polymer chain is in solution. I guess I can keep going. And you've got solvent molecules all around it. And so there is interaction between those solvent molecules and the polymer chain. We'll talk more about that in a minute. But the key thing to remember is that the polymer chain can express its energy as vibration. So this can be just simple vibration along the length of the chain. It can be a circular motion. It can be bending. It can be going in and out of the plane. There's a variety of ways a string can change in response to the amount of energy it has. And so this polymer chain is vibrating as in response to energy. If we go to 0 degrees Kelvin, it'll stop doing that. But as long as we're above 0 degrees Kelvin, it's always going to have some type of vibrational capability. Okay, and so this is important because it's part of what happens in the case of trying to dissolve polymer and solvent. If we increase the temperature, it makes sense that should be easier at higher temperatures. Why? Because both the polymer and the solvent molecules are moving faster. Again, polymers don't get hot, they don't get cold, they move faster, they move slow. That is what you should be thinking of in terms of energy. You have more notes someplace? All right, thanks. Thank you, all right. Might want one of those to play with now or later, up to you. Okay, and so what we can get when we increase the temperature are enhanced solubilities and increased saturation levels. This should make sense based on what we know, just salt and water. We get increased rates of solvation, meaning that the process can go more quickly when there's more energy available because everything moves around faster. And of course, thinking back to the plastic end of things, you also get increased likelihood of swelling because if the solvent's moving faster, it can penetrate and diffuse inwards more easily as well. Okay, so this, again, hopefully brings home the importance of temperature in these polymer-based systems. Okay, so why do we do this? Why do we worry so much about this? And part of this is historic. So we came up with all these different polymers in the 20s and 30s and 40s, and people started making enormous amounts of money off of these plastics, but we didn't really know what their structure was. We didn't have a good way of analyzing amorphous things. We still don't have the best technology, but we're much better at it than we used to be. And so what people wanted to do, though, was try to find out, well, is there crystallinity present in these systems or not? And so if you take a molten polymer and let it crystallize, you don't really see the crystals because they are too tiny. I know I keep showing you these nice microscope images, but they didn't know about a lot of that back then. And even if they did, they didn't know what they were looking at. And so what was done in this context was to dissolve things in solution, which gives you this maximum freedom. Remember the C1, C2, C3 model. Okay, make sure you're familiar with that. And because it has more freedom and the ability to move, it can pack into a single crystal more easily than if it's in a melt, where it has a ton of neighbors that keep it from doing what it can do when it has lots of freedom. Okay, and so what you end up with, in terms of crystal-wise, you end up with much less amorphous content. And so the question becomes, how do you take this bunch of spaghetti, which again has defined bond angles to worry about, and transform it into what you see over here? You see a bunch more of these. This is a single crystal. And I think this is like maybe 3 or 4 microns. It doesn't seem very large in the scheme of things, but it is probably 100 times larger at least than what you'll get in the melt. All right, and so what they did was they took these polymer solutions, dissolved them, and we talked about this last time. So like, 0.01 weight percent. Dissolved them and then slowly, very, very slowly, started cooling it off. And under those conditions, those dilutions, we started to see crystals. And so this is the first hint that crystallinity was even possible with these plastic materials. All right, these experiments. And so what we've got in this context is, let's just change color. We have polymer chains that, and I have to watch closely, that line up with each other and pack. Again, all the puzzle pieces have to be the same. All right, so they assume this crystalline nature, and then out beyond that, the polymer chains. So there's a couple different ways of looking at this. The simplest, least likely probably, but simplest way is that they fold very neatly into the next polymer chain. And so this process goes on and on and on, and what you've got is a boundary between the crystalline content, and this is where my lack of artistic ability looks bad, the crystalline content, which is here between the black lines, and then out here it's amorphous. So you cannot make those polymer chains bend and have them be crystalline at the same time. Hopefully that makes sense. We have to have puzzle pieces that fit into each other. These guys out here that are doing all this bending and looping back in, it's just not happening. All right, so even if you could nucleate the crystal the size of this table, which would be a phenomenal thing to do, one single crystal the size of this table, it would still not be 100% crystalline. Why? Because it's got this stuff out here. No matter how perfectly you do it, you're always going to have amorphous content. So at the bare minimum, you always have that. Okay? Hopefully that seems clear. So you've got, as it says here, these unincorporated leftovers that didn't make it into the crystal structure. All right. But again, it's a consequence of the fact that this is long chain matter, and it has to do this in order to keep folding. And so this very nice looking version of this is called the switchboard or adjacent reentry model. And so switchboards were used to conduct telephone communications, and they actually had people doing this. You've probably seen that in movies. And so when they first came up with this idea, that's what they named this adjacent reentry model. And again, the same thing holds true here. You have a boundary, which is easier to draw here, between the amorphous and the crystalline content in this system. So what's in the middle is still crystalline, and out here everything is amorphous. All right, and so this is very nice, very neat, very pretty, and very unlikely. All right, so you remember we talked about the fact that polymer chains have to have lots of energy and do all this bending and twisting, and the idea that every single one of them is going to go through this really nice, neat, simple loop is wildly unlikely. And so we get into more realistic systems called the irregular or random reentry model, where the polymer chains, we can still draw the boundary the same way. All right, but what's happening out here is the polymer chains are not behaving very nicely. They're looping around in whatever way their thermal energy dictates, and then maybe they go back into the crystal. Maybe they don't. Maybe they go off into infinity and never enter a crystal again. All right, so this is much more realistic. But again, the same inside the crystal is exactly the same, regardless of what happens outside the crystal. The structure is exactly the same. Any questions about that? All right, hopefully that makes sense. And then there's a whole bunch of different versions of this, and people spend a lot of time thinking about this and trying to decide, well, how much of this and how much of that do we have? And even to this day, we don't really have a good way of quantifying this. I can tell you how much crystallinity there is in a plastic, but I can't tell you what the amorphous content is doing. I can't tell you what the shape of it is. I can't tell you whether it's neatly re-entering or undergoing this looping, or if it's going off, as it shows here, it could go off into infinity. We don't know. We don't have a good method for estimating that. All right. But we do know it's probably something like this. All right, but keep in mind that out of all these models, remember the chain direction in these systems is the strong direction. All right, we'll come back to that later, but remember that there's carbon-carbon bonds, so that's where the real strength, if it comes down to it, when you really stress the systems, the chains are the strongest component of these systems, regardless of the fact that things are packed into crystals. Okay, and so we can look at what's called a conformational view of crystallinity, and so it helps us, and we'll keep doing this actually, it helps us to think about a polymer chain sitting down and packing very nicely next to its neighbor. In reality, things are probably more complex, because if you start with a random coil with no crystallinity, again, very dilute solution, and you start cooling it off, this is again using the simple view of solvent molecules as nice round spheres. You have this issue called Brownian motion. Does anyone know what Brownian motion is? So it used to be people knew the answer to that question. Nobody knows what Brownian motion is? All right, so Brownian motion is the interaction of solvent molecules with something else. In this case, we're looking at these solvent molecules and how they interact with the chain. And so if this is something simple like benzene, for example, you've got benzene molecules that are not long chain matter, and they're rattling around because they have their own energy. All right, they're not sitting there unless you, again, at 0 degrees K, things are moving, and they're moving very rapidly at room temperature. And so they're constantly banging into these polymer chains and making them move. So it's not just the energy of the chains alone, it's the energy of the solvent around it, and that energy is known as Brownian motion. Okay, so I can take nanoscaled alumina or metal particles, certain types, and put them in water, and under the light microscope you can see them dance around with nothing obviously making them move, and that's the water molecules slamming into those small particles. Here we have solvent molecules slamming into the polymer chain, helping it reorganize and helping it start to crystallize. And so what happens, again, in the real world, things aren't exactly the way we predict them, but you start forming helices in these structures. And that's where the crystallization really starts, where the puzzle pieces start fitting together, is inside these rounded structures that have the same spacing between the polymer chains. Okay. And so this goes on, and eventually you end up with something similar to what we talked about before. You have crystalline component, and outside that it's amorphous. Okay, and this is, as I said before, much easier in solution than it is in a melt, because there's lots of freedom out here for these polymer chains when they're not obstructed by other polymer chains present at high densities. Any questions about that? All right, so this is the 3D view of crystallization. We talk about it as if it's 2D, but reality, unsurprisingly, should be more complex. Okay, so shapes. There are a variety of shapes. This is one polyparadioxanone, which is a biomedical polymer that's biodegradable. And what you got in this case is this diamond shape. And so this is 2 micron bar. All right, so maybe this is 10 microns. This is considered a large crystal. All right, again, they had to work pretty hard to prove this, and then they spent a lot of time arguing at conferences and so forth. And so you get these nice diamond-shaped crystals, and then on top of them, you can also see smaller diamond-shaped crystals. Okay, so you guys have had nucleation and growth, right? Yes, kinda, you think, maybe? This is not a philosophy class. You've had nucleation, you've seen it before, all right? So this is showing you that you can have a large crystal, and then on top of that large crystal, we can have secondary nucleation and growth of smaller crystals. Okay, so we get nice behavior in the big crystal shape, and then we have some leftovers, maybe a neighboring chain got involved. It's hard to say exactly, again, what's going on. And so these crystals are forming on top of other crystals, and then nearest this you have more of a squarish looking crystal, and then we have, again, secondary nucleation and growth of other polydioxanone crystals on top of that. And in fact, what you're seeing here, if you look closely, it is a screw dislocation forming from those crystals. All right, so we do see this with crystalline matter. Again, don't worry, it's not important. It does happen, but it has no control over mechanical properties, believe me. Okay. And so these are the kinds of shapes they observed that help them prove that there are crystals inside these polymers, inside these plastics. And we will sometimes use the term single crystal interchangeably with lamella. So this is a polymer term. A polymer side calls single crystals lamella sometimes. I tend to go back and forth. Try to stick with crystals for the most part, but sometimes you'll see that word used. So if you do, then just realize it's a single crystal. And again, we can have a variety of shapes. Again, we have these screw dislocations inside these structures that results from how we have this process of nucleation growth and how it's favored. And we have a whole bunch of shapes here. So what we're looking at, again, for polyperidioxanone, this is starting to increase the solids concentration. So we went from 0.01 to maybe 0.02. And so what you're seeing is a higher density of nucleation and growth in these systems, which should make sense. In some cases, you get large crystals, and on top of that, you get a bunch of smaller crystals. All right, and this, going zooming out here, so that's a 2-micron bar. All right, so you can start to see that even in solution, we get some really tiny crystals. So we're getting these submicron, maybe in some cases 100 nanometers, and this is under the best conditions. All right, this is in solution, a little bit higher concentration, but still in solution. And so in the melt, things are even worse. And so this is one of the reasons why it's so hard to see single crystals in melt crystallized plastics, because this is considered big. Without barriers to polymer motion, you throw in a melt structure which is just surrounded by polymer chains, and crystallization is very limited. And so we get these very small nanometer-sized crystals that we more or less just recently have the ability to actually see. And so this was an important discovery for them because they couldn't really see these things in the melt. Okay, any questions about that? So this is why we worried about dissolution. And so thickness of these typically in real systems varies from 5 to 20 nanometers. All right, this is thickness, not just the lateral XY parameters. This is the actual thickness of them. And this is, of course, temperature sensitive. All right, so the amount of energy present determines how thick they can be. And so with molten plastics, think of them as being on the 5 nanometer thickness. Okay, that's 50 angstroms. It's next to nothing. That's a bunch of air molecules strung together. Okay, so these things are very, very thin, very hard to see. Now I'm going to invoke what's called, what I learned is supercooling. You guys are now calling it undercooling, right?
Yeah, we've heard of undercooling.
Undercooling. Okay. Yeah, it'll probably change back to supercooling, but anyway, so right now it's undercooling. So we're used to seeing this term. And undercooling can be expressed as delta T, where that is equal to, well, one expression for that is T actual minus T melting point. All right? And so if we have a low undercooling or very small delta T, this will give us the thickest crystals. Why is that? Yes?
I think I remember from one of the classes previously,
if you have the lower uncooling, it promotes growth more than nucleation.
It does, that's right. But why do we get that with polymers? Why is growth preferred with a polymer chain? Why would a small delta T give you growth preference? That's the correct answer, but why? Yes?
More heat to get the chains to move with each other.
Yeah, exactly. You are right next to the melting point. You're right next to TMP, which means it has the most energy. All right, which means the chains can move around, which means it's easier to incorporate a long length of chain into that crystal structure. So that's going to give you this end of the spectrum, the 20 nanometers thick. Woohoo! It's 20 nanometers thick, but it's able to do that because there's more energy available in the system. Okay, and also that's why you get more growth. Okay, hopefully that makes sense. So it's all about polymer mobility, the amount of energy in the system, whether it can express its desire to be as random as possible. All these things are bundled together in determining what's the thickest crystals. On the other hand, if we go to higher undercooling, then we get thinner crystals. All right, that means that delta T is larger. Okay, so from a nucleation and growth perspective, which process is now favored when it's a large delta T? Nucleation is favored, right. But on the other hand, if we think about it in terms of the energy of the polymer chains, when delta T is now large, we have less energy in the system. It's more difficult for the polymer chain to move around, and so you're going to incorporate things into crystal structures because of this delta G driving force, the enthalpy driving force. But what is going to happen is a relatively thin section or a short section of chain is going to be incorporated into that crystal. All right, and so that's going to drive you more towards the 5 nanometer range. So it's all about available energy and what the polymer chain can do in terms of crystallization. Lots of energy, thicker, longer sections of chain. Limited energy when you have high undercooling is going to give you thinner crystals. Yes?
In terms of a greater delta T, would that be positive or negative?
In terms of what?
Like what would be a larger delta T? So like if it's the difference of -1 versus 10.
Oh yeah, so
-10 versus -1.
yeah, so -10 is considered a large undercooling. Yeah, yeah. So small undercooling is like 0.1 degrees centigrade, that kind of thing. Okay, any other questions? Okay, and so as we go from 0.01 to 0.02 to, oh gosh, maybe we're going to 0.1 weight percent. What you're going to see is multiple lamella from a single nucleation site from non-dilute suspensions. And so I'm going to start out with one crystal, and these looks like sticks of gum, basically. And that guy, as you hopefully know, nucleated and grew from some point in space. Question, is nucleation and growth homogeneous or heterogeneous in real systems?
Homogeneous, ideally. Heterogeneous in reality is used to my experience.
Heterogeneous in reality. Okay, so we have mathematical models for homogeneous nucleation. In reality, we don't know if we ever get there, because if a piece of dirt is 10 nanometers in size, who the heck knows if it's there or not? So it's really hard to prove you ever have homogeneous nucleation. So what you have in this context is some speck of dirt, whatever it is, that allowed for nucleation and growth to occur, and then on top of that we have another polymer crystal, and then a third polymer crystal, and then a fourth polymer crystal, and so forth and so on. And so this is what you see in real structures. Of course, if you zoom in on it, we're talking about these crystal structures, but if you zoom in, then you'll see everything we talked about is still there. Polymer chains lining up with each other, and polymers looping in and out, and so forth, to form the appropriate polymer orientation needed for crystallization to occur. Any questions about that? Why are these guys all nucleating from the same spot? So we start out with, yes?
Heterogeneous, easy to nucleate, homogeneous.
Heterogeneous nucleation is easier, and you have polymer crystals to nucleate on. So you've got a site there which already exists as surface, which means the barrier for nucleation is now lower at that site. Okay, any questions about that? So this is slightly more concentrated. In reality, of course, if we go toward, and you've sort of seen this already, you go toward more of a melt structure, then you get, this is attempting to show you the spherulite on the outside growing in this totally amorphous medium. But if we zoom in on it, again, same rules apply. We have crystalline structures defined by these red lines, and they're all the same inside the red lines. And then outside of that, we have amorphous content. Amorphous content, amorphous content. Amorphous. I'll spell it out here. All right, so this is why even if we zoom out and we see those nice round spherulites growing in that melt, inside of that nice round spherulite, which consists of many individual single crystals, we have lots of amorphous content. Okay? So hopefully this is radically different from what you're used to thinking about in terms of grains, because there aren't any grains in these systems. Any questions about that so far? So we still have this same individual point of nucleation and growth, and then everything shoots out from that point. And in a real melt, this is a three-dimensional blob. Okay? Consisting of hundreds, if not thousands, if not maybe millions of individual crystals. Depends on the size of the spherulite. Okay? So hopefully that makes sense. And we get, in most cases, once the piece of dirt has been covered over, we get growth on a pre-existing nucleus. And of course, we just talked about this. Homogeneous occurs in the textbooks. It doesn't really occur in real life. It's always heterogeneous. And so what we're looking at in this context is a conformation matching the pre-existing crystallized polymer. So there was some initial heterogeneous nucleation and growth on whatever it was, and then we form a polymer crystal, and that serves as a template for further crystal growth, a phenomenon known as when something crystallizes using another crystal as a template, we call that, gallium arsenide uses it all the time. Nobody knows? Epitaxy? You guys seen that? Okay, some people heard of epitaxy before. Only one person told epitaxy. Okay, epitaxy is nucleation and growth, where the nucleation and growth is pattern matched to a pre-existing crystal structure. And so in microelectronics like gallium, they have a layer of gallium, and they force arsenide to grow on top of that gallium, and it's forced to follow the structure of the gallium, even though it wouldn't normally do that. All right, so in electronics, they do this all the time with very thin films. In this context, the polymer is just matching the structure of the polymer that's already there underneath it, and that's epitaxy. In case you haven't seen the word before, epitaxy. All right, and so we can attempt to present this in more mathematical terms. If we have a crystal that's growing and it's adding subunits consisting of individual lengths of polymer chain, and we can think about them as individual boxes that are extending this crystal structure in that direction. Okay, so we're taking amorphous polymer and incorporating it into this pre-existing crystal structure down here. All right, that should make sense. And it's doing that because of this epitaxy occurring at this interface. The interface A provides a surface that already exists, and so it doesn't have to nucleate and grow a new surface because there's already one there for it to match to. All right, and also pattern patterns itself to what's already there. So it makes the process much easier. So this is why you saw those big pictures, well, they look like big pictures of crystals, and they grew out in one XY plane. That's because they're doing this over and over again, if it's controlled correctly. Okay, and so this is the context. This is what we're trying to see happen. And so there's a couple of things we need to define here. One is the fold surface energy. And so I've been drawing these structures over and over again. So we have the polymer chains that are puzzle pieces matched to each other. And then outside of that, we have who knows what. Polymer chains can be behaving very nicely, or they can loop around, or they can go off into infinity, and another polymer chain comes in, and it goes off to infinity. Who knows what's going on? And that energy of that surface is called the fold surface energy, or gamma sub E. So that's this guy out here, this amorphous, poorly defined interface. On the other hand, we have gamma sub S, which is the side of the unit here. And this is what we're familiar with when we think about polymer crystals. Everything's nicely organized. All right, structurally everywhere it's the same, no matter where we look, and that has gamma sub S. It's much more comfortable with this because it's a much better defined energy. And what we're looking at, and we're adding these blocks, is N, which is the number of adjacent polymer chains added to the crystal. That's supposed to say crystal. And then L is the length of each polymer chain that will be crystallized. And so if we have low supercooling, all right, L is larger. If we have high supercooling, L is very small, just like we said before. And then we also specify A and B as width dimensions of the chain. And so we've got this pre-existing crystal structure. And again, we're adding these units, one bunch of it at a time. And we specify this dimension is B, and this dimension is L, and this dimension over here is A. All right, so L is a certain thickness of polymer chain that's being added to those crystals. Okay? So everyone sort of see that? Doesn't matter if you get this exactly right. It sorts itself out. And so the thing is growing out in that direction and incorporating more L's into its structure as time goes by. Okay? So with that as the context, we keep doing the energy analysis. And so, what you guys have hopefully seen some of already, let me know if not, we have two contributions to nucleation and growth. One is the surface, so we cheat, we have some epitaxy going on, so we don't have to create that surface, but outside of that we have to create new surface. All right, and so for each block that's being added, we have this 2Bl times gamma, all right, the two surfaces being created, and the surface energy for the crystalline structure. And then as we move in the fold surface direction, we have A times B times gamma sub E. All right, so we don't have just one crystal surface to worry about. We have two of them that have different energies. And every time we add one block, we add another contribution, okay? And then we also have the volumetric contribution, which is NABL, which is the volume of each block times the free energy of nucleation and growth in this structure. And again, we learned about this a couple of lectures ago, where this is an enthalpic contribution. And then we put everything into the hopper, and so we have the volumetric and surface contributions all added together, 2Bl gamma sub S plus 2NAB gamma sub B minus 2NABL delta GV. We approximate delta GV, as we are often happy to do, as a delta HV times delta T divided by this melting point, where this delta T is, in your terms, undercooling, or this T minus Tm. Okay? And so this captures everything, both surface and volume, and tries to utilize that to give us a sense of what's important in these systems. And so for a set N, the energy change, the free energy change, is a maximum when L is small, it becomes a minimum as L increases. And this should sort of make some sense based on what we talked about, because if L is small, then there's not a lot to be gained by crystallizing, all right? So nucleation is not really that favored. Growth is, but nucleation isn't so much, all right? But as L increases, then maximum L is small, meaning that it's easy to nucleate growth with less energy for it, and minimum as L increases. For a critical chain length, L naught is needed for the free energy change is equal to 0 or negative, depending on how we're producing this. And it shouldn't be surprising that N is usually large, where if we're adding many chains at one time. So you have a 2 micron size crystal, all right, but remember we're talking about 1.54 angstroms unit lengths being added, so there's lots of chains going into that crystal. And anything that doesn't have N in it, all right, becomes irrelevant. So the 2Bl gamma sub s is just left behind because it's just the bookends on these structures. It's not really anything relating to the number of structures being added. And so this delta G sub n is then equal to 2 NAB gamma sub e times NABL times the quantity delta H V times delta T divided by the melting point. And if the nucleus is stable, then we can set everything together, and it tells us that this critical length L is equal to 2 times the fold surface energy of all things, not gamma sub s after all, times the melting point divided by the enthalpy of crystallization, which we learned about before, and the undercooling, in your words. All right. So out of everything that's in this equation, what do we have control over? Change in temperature. Can we control the melting point of the polymer? No. Can we control the fold surface energy? No, we have no control over that. All right, we have no control over the enthalpy of the crystallization reaction. The only thing that we can tweak is delta T. All right, and so our ability to control this process depends entirely on our control over temperature, and thus this critical chain length L naught. All right, so that should make sense based on everything we've talked about so far. So we have this process of nucleation and growth driven by the amount of available energy and how long we're willing to wait in terms of the crystal slices that form. Any questions about that? Okay, so getting back to how these things look. First off, again, these are structures made of spherulites, and if you use the hot stage microscope, then we can kind of see what we've already talked about, which is where we have this initial nucleation and growth event here in the very, very beginning. So some speck of dirt is what started this off. And then we have waves of crystals shooting out away in all directions. This is 2D. But imagine the same thing is occurring in 3D. Okay? And so we have all these crystals that are growing, keep growing until it meets its neighbor, which is also doing the same thing. All right, so in 3 dimensions, we have these big globs that grow, and they run into each other, and they make flat surfaces, which look like grain boundaries, but are not grain boundaries, because there are no grains. All right, they do look an awful lot like grain boundaries. And in plane polarized microscopy, we have these Maltese cross patterns, and so you can see where these spherulites run into each other. We actually get some secondary nucleation and growth going on in these other areas that are kind of trapped. So that's one of the differences between grains and spherulites. But the radiating nuclei are clearly visible, so you know where everything began in these systems. And so this again is an effect of light extinction. This Maltese cross pattern is the passage of light is eliminated by the process of extinction, where we get destructive interference, and that's where the dark comes from. The passage of light is enhanced, which gives us constructive interference, and that's where we have the light areas. Again, it doesn't say anything about the polymer. There's no such thing as light polymer, dark polymer. This is an optical effect. Again, if I rotate this, the Maltese cross pattern will stay exactly where it is, all right, which is a dead giveaway. All right, so this is something that is just a purely optical effect. It does not exist in real structures. And unlike inorganics, where any of you guys have had the pleasure of looking at intergranular fracture and transgranular fracture and those kinds of things, if you ever do any work on failure analysis, that becomes a very, very big deal because it determines who's at fault in some cases for people dying. So anyway, but with polymers, you can't really get much out of fracturing polymers. Even if we do what's suggested here, you take it and cool it down into liquid nitrogen conditions, which is only 77 centigrade, polymers still move around pretty good at 77 centigrade. All right, so we don't really get brittle fracture with these polymer-based systems. In the case of PTFE, however, because it's slippery stuff, you can actually get, under liquid nitrogen conditions, you get some suggestion of the spherulites that exist inside that PTFE. It's one of the few polymers that does this, because again of its interfrictional characteristics between polymer chains, and you can sort of see some of the aspects of polymer chains and so forth moving around as the crystals are deformed. So in there's some crystals. They're kind of hard to see, but they are there. But it's all zoomed in, and usually, as I said before, fractography of polymers gives you no information whatsoever. All right, and this is one of the things that frustrated people back when they were trying to look at what are plastics, what is their structure. It didn't do what inorganics do. You can't look at transgranular fracture, because first off, there's no grains. You can't even look at transspherulitic fracture because it doesn't cooperate like grains do. And so we have these structures. We call them spherulites. We have the nucleation site. We have the boundaries, which eventually run into each other. And between those lamella, we have polymer chains. And so one thing to keep in mind, it's very, very different from the case of grain boundaries, is the polymer chains were there first. All right? And all because we're growing things in them doesn't mean the polymer chains stop or start differently. All right, they were there at the beginning. The crystals grow into them, and so you can have polymer chains that, again, start at one end. Not giving a place to do that, but it could start up here, go through the crystal, go through the amorphous, go through the crystal again, go through the amorphous, go through the crystal again, and then go off into infinity. All right, so they were there first. So at the macro scale, you see the spherulites. Bless you. There's amorphous material in between the spherulites. There's also, if we zoom in on that spherulite, you see that there's amorphous material in between the crystals within that spherulite. And if you zoom in even further, you can see more amorphous material even in between these crystalline areas. And so there's plenty of places where crystallinity can be interrupted by amorphous content. So they are very different from grains, which doesn't have anything like this. Okay, so one thing to keep in mind, again, one of the big differences is, well, let's see. So what is a grain boundary? In crystalline metals and ceramics, what's a grain boundary? Is there a legal definition that you guys carry around in your heads, or do they even teach those anymore?
Kind of just what it sounds like.
Yeah, but what is there at the grain boundary? What exists at the grain boundary?
Mismatch.
Say what?
Like a mismatch of orientation.
A mismatch of crystalline orientation is right. Have you ever heard that it can be represented as a plane of Shockley dislocations? You've heard that one? Okay, good. So you still teach that one. It's often also called a region of local atomic disorder, all right, because there is no order when those two orientations meet. Some people call it a vacuum because there's really nothing there. So it's a very distinct event between two very different orientations. In the case of spherulites, things are very different from that because we have what we see. First off, if we zoom out with our plane polarized light, we see a boundary. It says, there's the boundary. Is it like a grain boundary? No, not at all. Not in the least. So there's a couple of reasons why. We have individual crystals that are stopping and starting, nucleating, growing, and they're reaching this area. And they don't necessarily stop just because somebody sees something in the microscope at a much higher magnification. And then you have the other side, the other spherulite, and that has small crystals that are also reaching that boundary and probably extending over it, because again, they don't care what the person at 30,000 feet is seeing. They're going to do what they're going to do. And so you have this phenomenon known as interdigitation that's occurring. At this interface. And what that means is fingers coming together, all right? Fingers extending across the boundary. So we have that crystalline component, which pays no attention to what the guy at the microscope is seeing. They They don't stop just because there's an optical boundary there. Again, the optical boundary is an illusion. And then, of course, we also have the fact that the polymer chains were there first, and they don't pay any attention because they were there first. So the whole process of nucleation and growth doesn't change the fact that it's occurring inside polymers. And so you can have multiple polymer chains that are going back and forth across these interfaces and mixing and doing whatever it was they did before crystallization ever happened in the first place. Okay? Very, very different from a grain boundary. You know, I fracture a metallic ceramic, and if the circumstances are right, I can see the grain boundary very, very cleanly because it's a weak point in the structure. Here, not so much. All right? Any questions about that? Hopefully that all makes sense. Okay, and so we can sort of see these things if we start zooming in. This is, what is that? Hdpe, thin film. And there's another polyethylene here. And so you're looking at these spherulites meeting, and you see regions where the crystallites kind of cross these boundaries. And they're doing all sorts of interesting things. This is a better one. You can see two spherulites meeting, and in this region where they join up, there's crystalline structures that are being stretched between the two spherulites. All right, there's polymer chains here you can't see because they don't diffract light, and so it's obviously a very different situation at an interspherulitic boundary versus a grain boundary. Okay. Any questions about that? Hopefully that all makes sense. All right, and so putting all this together, we can start to think about a mechanical view of what happens when we deform these polymers. And this is something we'll come back to. I call it the clock diagram. You'll get sick of hearing about this. You start out with a semicrystalline plastic under load. You apply, using your tensile frame, you apply tensile load to it, and that load, as it's applied, is going to not so much deform the crystalline part, because remember they're little rocks, again, quote unquote, all right, but the amorphous part, which has no structure, is the first thing that deforms. And so you start stretching out the amorphous component, and you keep increasing the load, and you stretch that amorphous component out some more, and then at some point that amorphous component becomes so stretched that it starts pulling on the crystal structure, because that's the strong chain direction as it goes in and out of that crystal structure. And when it does that, it starts to fracture those crystals. Okay? And the material in between these fractured areas essentially melts, quote unquote. It goes from being crystalline to amorphous. It has to, in order for this process of sliding to occur. Okay? Does that make sense? And then as we keep extending this further and further, then we can really fragment things. And so we have little crystals here, and then amorphous in between them, and crystals here, and amorphous, and so forth. Okay, but this is the clock diagram. This is how we can think about these plastics deforming and the microstructure that is rearranging dramatically as we start straining this. We haven't broken any polymer chains at all. All right, we've broken and reformed 1 million secondary bonds, not covalent bonds. We haven't broken any chains. Okay, any questions about all this? All right, so see you guys on Friday.